All right, welcome back. This is part 2 of our series on the regulation of cardiac output. We previously discussed extrinsic regulation, things like the autonomic nervous system, endocrine signaling with epinephrine, and also baroreceptors, the baroreceptor reflex, and homeostasis with blood pressure. And in this video, we'd like to focus on the intrinsic regulation of cardiac output. In other words, how the heart actually controls itself. And this is pretty fascinating. Consider an experiment done back in 1964, so a few years back. In this experiment, researchers took greyhounds, racing greyhounds, and raced them around a track and measured their total speeds. And then they took those dogs and they actually denervated them. In other words, they cut the nerves going to the heart. The sympathetic and parasympathetic systems that we talked about in the last video, gone, ablated. And then they raced the dogs again. What would you predict to happen? Without sympathetic innervation, would you predict the dogs to go slower? Maybe the super dogs go faster? And what the researchers found was that the dogs ran at the same speed. There was little to no change, statistically speaking, in the speeds that they ran, even though their hearts were no longer connected to their brains. Now, some of that certainly is going to be attributed to the fact that epinephrine is an endocrine signaling molecule. This doesn't come from the brain, right? It comes from the adrenal glands, and it's still going to be in full force. I'm exercising, I'm getting epinephrine released from the adrenal gland. It's still binding to beta-adrenergic receptors on my heart, causing the heart to beat faster and stronger. But that can't account for all of the performance that they saw. And what they found, and what I'd like to accomplish in this video, is to help you understand what they found was that increased end diastolic volume led to increased stroke volume. And I want to make sure we understand what that means. Now, to understand that, there's a few things that we have to remember. First of all, from our last video, we saw that stroke volume, well, let's define end diastolic volume first. End diastolic volume, this is when the ventricle is filled. This is the amount of blood in a filled ventricle during isovolumetric contraction. And then the stroke volume, remember we define this as my end diastolic volume, EDV, minus my end systolic volume, ESV. So how much blood I had before I pumped, and then how much blood after I pumped, the difference is going to be my stroke volume. In other words, this is the amount of volume that was actually ejected. Now that we've defined those, let's go back to what we just said. We said the increased end diastolic volume will lead to increased stroke volume. In other words, the more blood coming into the ventricle before it pumps yields more blood actually being pumped out. Now, you might initially say, well, that makes sense. More blood comes in, more blood has to go out. But how does more blood go out? Remember, stroke volume is by definition proportional to the strength of the contraction. The reason I have a stroke volume is because there was a force generated with contraction. And so what we're really saying, if we were to rewrite this, we would say that if there's an increase in blood entering the left ventricle, then the heart pumps harder. In other words, there's an increase in the force of the contraction, simply because there's more blood in the heart. Now, to better appreciate what this looks like, let's see if we can draw a picture. Similar to the cardiac cycle, let's put pressure, specifically left ventricular pressure, on our y-axis. We would see this, of course, max out, an average person right around 120. This is measured millimeters of mercury. And on the x-axis, we're going to do something different. Instead of time, let's do left ventricle volume. Now let's start maybe with our end systolic volume. If you remember from the cardiac cycle, we've just gone through isovolumetric relaxation. And so my pressure is low. We're going to start really far down here. And with a volume of, about 50. And that's where we're going to start. Now remember, as we fill, we're going to be increasing in pressure slightly, not much. We've got some passive filling mostly. And then at the end, we might have just a little bit of active filling. Pressure goes up. And right at this stage, the mitral valve closes. Right? We've increased in volume, but that's only seen as a slight increase in pressure. Then, of course, we've got our isovolumetric contraction. We're not going to change volume at all, right? Volume is fixed, but pressure is going to skyrocket. So we see this go straight up. Now remember, the aortic pressure is probably going to be down around 90, 95, and as soon as the ventricular pressure exceeds the aortic pressure, we're going to open up the aortic semilunar valve. At this point, volume is going to drop during the ejection phase. Pressure will continue to climb for a little bit until we max out right at that 120, and then we're going to start to fall pretty fast. And then, of course, what's going to happen? Right here at this point, the semilunar valve closes. And then, of course, we got isovolumetric relaxation. Because we're isovolumetric, the doors are both closed, so the volume isn't changing, but we're going to drop in pressure all the way back down to where the mitral valve opens. And now, volume speaking, we're back at end systolic volume. So again, this is interesting because if this right here defines end systolic volume, and this point over here defines my end diastolic volume, the reason I like this picture is because it shows us that the difference between these two is the stroke volume. So this is just a classic pressure volume curve for the heart. What we want to explore is what happens when end diastolic volume increases. In other words, what if we extended this volume out here further to the right? Maybe that's a bit of an exaggeration, but you know, where normally we were ending at 120, maybe we got to 127, 128, maybe even a little bit higher than that. Hopefully your first question is, well, where did the blood come from? How can we actually increase the amount of blood flowing back into the heart? The cardiac system, the whole vascular system, is a closed system. Well, to understand that, we have to understand a term called venous compliance. And the easiest way to understand venous compliance, 2 words: stretchy pants. Now remember, we're talking about venous compliance. A key difference between arteries and veins: arteries are wrapped in a lot of smooth muscle. They're thick. They don't stretch a lot. I can regulate based on vasoconstriction, vasodilation, the size of these by smooth muscle constriction, smooth muscle relaxation. Veins, not so much. Veins don't have a lot of structure. They don't have a lot of smooth muscle, and therefore I don't regulate their tone very much. Compliance just describes their ability to expand, to stretch. And where I want you to think about this happening is in your legs. Consider right now, are you sitting? Maybe you're lying down. If you're not exercising, if you're not walking while you're listening to this, then guess what? You don't actually need all the blood that's circulating in your body. And so what happens? Some of it will actually sit in your legs. Gravity will pull it there. And that's okay. Venous compliance is a system where I've got reservoirs of blood in my legs that really I'm just kind of not using. Now, we feel these effects if we're not careful. I'm sitting in a hot tub and all my blood is in my legs, and then I stand up really fast. Well, where did I leave that blood? It's still in my legs. And then the baroreceptors that we talked about in the last video sense low blood pressure. Your heart tries to pump really fast, and maybe you won't pass out, but sometimes you pass out because it can't restore blood pressure fast enough. We also see problems with this in individuals suffering from deep vein thrombosis, where because the blood is hanging out in the veins and it's not moving very much in these reservoirs that we talked about, it is at a higher risk of clotting, and getting blood clots in your legs in the deep vein thrombosis can be very painful, and in some extreme cases even life-threatening, as those blood clots can break off and move to the lungs and cause pulmonary embolism. And so individuals suffering from that, or just from varicose veins in general, what do? They wear compression socks that reduce venous compliance. They make sure that blood actually isn't pooling in your legs as much as it normally would. Now, for the rest of us that aren't thinking about that, venous compliance is a normal part of daily life. But when I stand up to walk, to exercise, now to start running, what happens? As I flex skeletal muscle in my legs, that skeletal muscle squeezes on those veins, and veins are all driven by backflow valves anyway, and so I squeeze all that blood out of the reservoirs and back to the heart. So why would I have this increase right here in end diastolic volume? Well, because now I'm exercising, now because I'm moving, and I've taken that blood that was pooled in my legs and I've returned it to the heart. And so the amount of blood now going through the heart increases. Now, what I can hope you visualize is if I don't pump harder, then my stroke volume stays the same. And if all we had was that same stroke volume, say going about that far, you can see this gap right here. All of a sudden, I've got a lot of blood left over in my heart that I don't want there. That's what we're talking about. And the mechanism that drives this is called the Frank-Starling mechanism. So here we've seen increased venous return that led to increased end diastolic volume. But what we see, we'll go through the process. We still have our isovolumetric contraction, but we actually generate enough force to return all the way back to the original stroke volume, or excuse me, the original end systolic volume. And what that means is that our new stroke volume is greatly expanded. So now let's go back up and look at our definitions. With increased end diastolic volume, we get increased stroke volume. That is the Frank-Starling mechanism. And we've just shown it in picture form. Now what I'd like to do is just take a few minutes to offer a hypothesis for how we think this is happening. How the heart can actually pump harder simply because there's more blood in the ventricle. And it comes down to stretch. Now to understand this, we need to go back and we need to look at a sarcomere. We don't want to detail it too much. You can go elsewhere to find the details on this. But the sarcomere is going to be made of two bordering Z discs. We've got some thick filaments, and we've got some thin filaments. Let's label these really quick. Now, during muscle contraction, remember what happens. Remember, myosin heads at the end of the thick filament would reach out and grab the thin filaments and pull them toward the midline. So we will see the Z discs move inward. And with that internal movement, we can see how much the sarcomere actually was displaced. If we highlight the original location, then everything here in green shows the displacement and therefore the force of the contraction. Now, what might it look like with increased end diastolic volume? This is the Frank-Starling mechanism. Let's start at the same place, but this time, remember, what do we have? We've got increased venous return, and that leads to increased stretch. Now, the idea is, with that stretch, what have we done? We have optimized the overlap between our thick and our thin filaments, so that when we contract, if we now look at the total displacement from where we started to where we finished, we can compare that total displacement here with the increased end diastolic volume causing stretch of the ventricle, or under normal conditions here. The idea simply is the optimal overlap of thick and thin filaments maximizes cross-bridge formation, and that optimal overlap leads to a more forceful contraction, and therefore an increase in stroke volume. So in summary, the intrinsic regulation of cardiac output is primarily defined by the Frank-Starling mechanism, which says that increased end diastolic volume will lead to increased stroke volume. And this is likely to do with optimal overlap between thick and thin filaments, placing the sarcomere in the most efficient state to maximize cross-bridge formation. And with more cross bridges, there's more force generated and an increase in stroke volume.